When we talk about orbital mechanics, it can seem pretty complicated, right? But what if I told you there's one single number that kind of rules them all? One value that can tell you almost everything about the size and energy of an orbit. Today, we're going to pull back the curtain on that number, the semi-major axis. Yeah, I know what you're probably thinking. How can one number possibly define all these different orbital shapes? I mean, you've got perfect circles, and then you've got these long, stretched out ovals. It just doesn't seem possible. Well, let's break it down, starting with the simple geometry. All right, first things first. Let's just look at what this thing is geometrically. We'll get to the cool physics stuff in a minute, but for now, let's just start with the shape. Okay, so this is actually super straightforward. Just picture an orbital ellipse. The first thing you do is find the longest possible line you can draw straight across it, through the center. That line is called the major axis. Now, all you have to do is take exactly half of that length, and boom, that's it. That is the semi-major axis, and we usually just call it A. So for an oval shape, that makes total sense. But what about a perfect circle? Well, think about it. For a circle, every diameter is the longest diameter, right? They're all the same. So half of the diameter is just the radius. Yeah, the good old radius r. So for a circular orbit, the semi-major axis is a concept you've actually known about for years. Okay, so the geometry is pretty easy, but this is where things get really interesting. Because the semi-major axis isn't just about measuring a shape. No, it has a much, much deeper physical meaning. It turns out that in physics, the semi-major axis is a direct measure of an orbit's total energy. That's the big secret. It's the one parameter that tells you the entire energy state of that satellite or planet. And that insight is what makes A so incredibly powerful. And the relationship here is super intuitive. A bigger semi-major axis means the object has more orbital energy. It's freer, it's less constrained by gravity. A smaller A means the opposite. It's got less energy and it's more tightly bound, more closely hugged by the body it's orbiting. So here's a fantastic way to think about it, kind of a mental shortcut. We know a satellite's actual distance is always changing in an ellipse. Sometimes it's closer, sometimes it's farther. But you can just think of the semi-major axis as its average distance. It's a beautifully simple way to visualize the orbit's overall scale. Okay, so if A represents energy and this average distance, what are the actual real-world consequences? Why do people call this the master number for any orbit? Well, it all connects together perfectly. A small semi-major axis means you've got lower orbital energy, a closer average distance, and, importantly, a shorter orbital period. On the flip side, a large A means higher energy, a farther average distance, and a much longer time to complete one orbit. It's a direct trade-off. And that last point about the orbital period, that is arguably the most important consequence of all. The semi-major axis directly determines it. If you know the value of A, you know exactly how long a satellite takes to circle the Earth. It is a direct and incredibly powerful link. All right, enough with the theory. Let's make this concrete. Let's look at some real-world examples that you probably use every single day. Just look at this chart. The difference is huge. You've got satellites in low Earth orbit, or LEO, with a semi-major axis of about 7,000 kilometers. Now, compare that to the GPS satellites you use for navigation. They're way out there at around 26,600 kilometers. That massive difference in A has a profound effect on how they behave. And here is where it all clicks into place. Because those LEO satellites have that small A, they zip around the Earth in only about 90 minutes. That's it. But with its much larger A, a GPS satellite takes around 12 hours to circle the globe. You see? The size directly sets the speed of the orbit. So let's sum it all up. The crucial point, the thing to really take away from all this, is that the semi-major axis is so much more than a line on a diagram. It is the master variable. It's the one number that defines an orbit's size, its energy, and its period. And that leaves us with a pretty fascinating final thought. We've just seen how one single, elegant number can define so much about an object's journey through space. It really makes you wonder, doesn't it? What other simple, powerful numbers like this might be out there, quietly shaping the complex universe all around us?